Class D. Unit circle. So the unit circle specifically gets its name because the radius of the circle is 1 unit, or just 1. So the unit circle is a circle of radius 1, this pen is trash, centered at the origin. I'm going to try and draw it kind of big. It's a pretty good circle. So there's the origin, and my radius is 1, meaning this point here is 1, 0. This point here straight up is 0 in the x direction and 1 in the y direction. This point over here to the left is -1 in the x direction and 0 in the y direction. And this point down here is 0 in the x direction and -1 in the y direction. So the nice thing about the unit circle is it's going to allow us to find or evaluate the trig functions of all the angles we talked about yesterday without actually using a right triangle. I mean, you're still kind of using a right triangle, but you don't have to. So here's what we know about the unit circle. Yeah, I want to say this first. So any point x comma y on the unit circle, how do I want to say this? Yeah. Has the coordinates cosine theta, sine theta. And I think the picture will help. So here's what I mean. If I pick, say, this point right here, that coordinate, which I can call x, y, is also going to have the value cosine of theta, sine of theta, where theta, which I maybe should have started with, is the angle you get by measuring in the usual way, right? Where the angle is in the standard position. Whoops, so someone just left and came back. Okay, anyway, so this point here, x, y, whatever this angle is made by going along this arc up to that point, this point x, y is cosine of that angle, comma sine of that angle. And we can see this, I think, without too much difficulty by dropping a perpendicular. So I drop a perpendicular always to the x-axis. This base of this triangle, well, if I'm calling this point x, y, it means I've gone x in the x direction. And if I call this point x, y, it means I've gone y in the y direction. So the length of the base is x and the height of the triangle is y. And then the radius of this circle is 1, which means the hypotenuse of this triangle has a length of 1. So this is true for a unit circle, right? Again, unit circle, the radius is 1. Now we can use this triangle to define the trig functions on the unit circle. So I look at this triangle, here's what I'm going to get. Sine of theta is the opposite over hypotenuse, which is y over 1. But anything divided by 1 is just itself. So that's just y. Cosine of theta is x over 1, which is just x. Tangent of theta is opposite over adjacent, which is going to be y over x. And then the reciprocal functions are still the reciprocal functions. Cosecant of theta is still hypotenuse over opposite, which is going to be 1 over y, or just the reciprocal of sine theta, which is 1 over y. Secant of theta will be the reciprocal of cosine, which will be the flip of x over 1, which will be 1 over x. And cotangent of theta will be the reciprocal of tangent, which will be the flip of y over x, which will be x over y. So this is one way of thinking about the trig functions. And I will point out something and then I will tell you what you're, so we could use this to evaluate the trig functions we were evaluating yesterday. For example, in fact, so I could draw the picture here, but I think it's going to be more beneficial to all of you if I show you a nicer picture. So obviously any of you can Google a unit circle and you find like 1,000 pictures on the internet. Let me share my screen. Let me show. Really? Come on. 1 second. I'm having a challenge here. I want to share desktop too. Okay. Sorry. I want to make sure it shows the right thing. Oh, you're a liar. I see. Okay. Fine. 1 sec. Let me do this. Okay, I think I can be smart here. Yeah, now I'm going to share my screen. Yes, okay, good. So here are some unit circles. So first we have this, and hopefully everyone can see this all right. This one on the left is just showing us the thing I just drew, right? That if you have an angle theta measured from the positive x-axis, then the point where the terminal ray, which is that line there, intersects the circle, so it gives you the point on the circle, that point x comma y has an x coordinate of cosine theta and a y coordinate of sine theta. And what I want to point out is that if you look at the unit circle here, for the special angles that we are familiar with, all of those angles have the cosine and sine value as the point. So that point, right, so if I'm looking at the angle at this other picture now, can you guys see my like cursor when I move it around like that? Yes, okay. So if you look at the angle pi over 6, I bet there's a way to make my cursor bigger, but I'll figure that out maybe another day. So this angle pi over 6, the x coordinate is √3/2 and the y coordinate is 1/2. So we could use that to say that cosine of pi over 6 is the square root of 3/2 and sine of pi over 6 is 1/2. Now, that's not the way I want to do it personally. But for some people, I've definitely encountered students in the past who it was just easier for them to memorize the entire unit circle. If that's the way you want to do it, that is perfectly fine with me. I don't care how you remember what the trig functions of the special angles are. I just care that you are able to remember what the trig functions of the special angles are. So if you want to do it this way, where you memorize this entire circle, that is fine with me. So let me show you kind of what I mean by this. I suppose I'm gonna. So I'll post these unit circles on Canvas so you can have them. Obviously, you can also just Google one. But if you want to use this one specifically, I will put it up there. I like this one because it's kind of color coded a little bit. Actually, there's another one I have that's better. But so for example, let me stop sharing my screen here. If I said, you know, I want to find sine, cosine, and tangent of 5 pi over 6, one way you could do it if you wanted to, not the way I'm going to do it in general, but if you wanted to, you could say, hey, I know that for 5 pi over 6 on the unit circle, that's the angle that's over here. And I remember, because I have memorized the unit circle, that that coordinate is negative √3/2 for x and positive 1/2 for y. So then you could say, okay, sine of 5 pi over 6 is the y value, which is 1/2. Cosine of 5 pi over 6 is the x value, which is negative √3/2. And I think tangent's a little more difficult this way, but not a ton. Tangent of 5 pi over 6 is the y value divided by base. So in fact, this is one of the other reasons it's nice to write it as sine, cosine, and then tangent, because sine is the y value, cosine is the x value, and tangent is the y value divided by the x value. So it's literally just this over this, which you already kind of have written down. So it's going to be 1/2 divided by the negative square root of 3 over 2. Now, when you have a fraction divided by a fraction, if the denominators are the same, each of those denominators cancels out. You can just cancel them out automatically, or you can show the work. Right? Showing the work, I would flip. Some people say copy dot flip. Some people say you multiply by the reciprocal. Right? That's going to be 1/2 times you, right? You copy. I can't do it. I've never done copy dot flip. Dot. You flip it. You get 2 over negative root 3. The 2's cancel, and you get negative 1 over root 3. And if we rationalize, we get negative root 3 over 3. This is certainly a perfectly valid way of finding sine, cosine, and tangent of 5 pi over 6. It is not the way I would do it. The way I would do it instead would be this, would be to say, okay, the reference angle is pi over 6. And I know that sine of pi over 6 is 1/2. Cosine of pi over 6 is root 3 over 2. And tangent of pi over 6 is 1 over root 3, which is root 3 over 3. And then I would use that knowledge along with the quadrant, right? I know I'm in quadrant 2. So I know that sine is positive, right? All students take calculus, sine is positive, tangent, cotangent are negative. So I could use this. Sorry, I'm kind of out of room where I want to have room. I'm going to go up over here. And this is kind of terrible. I'm sorry. So you say, okay, so using this along with the quadrant 2, I know that sine of 5 pi over 6 is positive 1/2. I know that cosine of 5 pi over 6 is negative root 3 over 2. And I know that tangent of 5 pi over 6 is negative root 3 over 3. So I personally still like to use the reference angle method when I find the trig functions of the various angles in other quadrants, but you don't have to do it that way, right? If you want to just memorize this unit circle, that is perfectly fine. Now, honestly, I kind of do it this way, even though I don't. I've really kind of memorized the first quadrant of the unit circle, and then I just remember that the other angles in other quadrants, I remember which angle has the reference angle, and I'm like, oh yeah, in the first quadrant, it's these values, and then I just change the sign based on if I'm in the second quadrant, the third quadrant, or the fourth quadrant. So the reason we're talking about the unit circle is not so much because of this, right? You could totally use it to find, tangent of 5 pi over 4 or secant of 11 pi over 6 by saying, well, okay, secant of 11 pi over 6, I know that cosine of 11 pi over 6 is positive root 3 over 2. So secant of 11 pi over 6 is going to be the reciprocal, which is 2 over root 3, and then we would rationalize it. That's not really what we're here for, though. So again, I just want to reiterate one more time. You can find sine, cosine, tangent, cosecant, secant, and cotangent of the, of any angle in here the way you want, either by just memorizing this or by doing what we were doing yesterday, finding the reference angle, finding the quadrant, etc. However, there are some angles in the unit circle where we can't use that method, specifically the quadrantal angles. So I was just saying how we can, we can find sine of, we can find sine of 2 pi over 3 by using the reference angle for 2 pi over 3, which is pi over 3, and then by determining what quadrant it's in. But quadrantal angles like pi over 2 or pi or 3 pi over 2 or 2 pi, those angles don't have reference angles, right? To have a reference angle, you can't be an angle that ends on one of the axes. And so for those angles specifically, we don't have a choice. We cannot use the method we were using yesterday to find sine or cosine or tangent of any of those angles. We are forced to use the unit circle if we want to find, say, tangent of pi or cosine of 3 pi over 2. So that's what we're going to do right now. Oh, and I should stop sharing my screen so you can actually see me instead of what's on my screen. Okay. Also, just as a reminder, today is the last day of class this week, right? We don't have this class tomorrow. I'm sure you guys have other stuff you have to do. I will also remind you, since I think everyone is here now, hopefully, there is a quiz 1, that is, I think it's due by some Saturday evening at 10 p.m., I want to say. You have, it should become available today, I think at 4 p.m. You have, and from now until then, you only get an hour to do the quiz. So once you start the quiz, you only have an hour. It really probably shouldn't take very long. I would imagine the longest it would take is probably a half hour. Probably maybe even less time though. I think it's only, I want to say it's 5 or 6 questions, so it's not too long. It's definitely not like your homework assignments. My intention for the quiz is for you to do it without using a calculator or other resources. That said, obviously I cannot police you. You can do whatever you want, to be perfectly frank, and nothing bad is going to happen. But really, I mean, this class is pass no pass, and we're here to kind of, the point of this class is so that you actually learn the material, right? So if you're going to take the quiz, please try and take the quiz without using any outside resources and see if you can do your best. Because really not doing well on one quiz probably won't make the difference of passing or not passing this class. My what's the word I'm looking for? I would imagine that everybody's going to pass this class. That is my goal for the class. I think all of you are capable of passing the class for sure. Right? I guess I haven't talked about passing the class, right? The class is pass no pass. The passing grade is getting 70% or higher. I think everyone is very capable of getting 70% or higher. So I certainly imagine everyone will pass this class. That said, take the quiz, do your best, try not to use outside resources. All right, and again, you will only have 1 hour once you start it. So make sure you have the time set aside to do it, because I'm not positive, but I think once you start it, you can't like stop it and have the time and have the clock stop. I think you like have an hour once you start the quiz. So just be aware. All right, so back to what we were doing, the unit circle. I want to find the 6 trig functions of theta equal to pi over 2. I think this pen is starting to suck as well. Got an okay green one over here. So when I want to find the 6 trig functions of a quadrantal angle, I'm going to draw the unit circle. And I'm really going to draw like a lazy unit circle. So there's my unit circle. And all I really care about on the unit circle are the 4. So I care about the 4 points. And I'm going to say something that I've said for a while, and it always sounds terrible. I care about the 4 corners of the circle. Yes, I know circles don't have corners. They are round. There are no corners. But it's a lot easier than saying like the 4 directions of the circle or the 4 whatever. Saying north, south, east, west of the circle. I'm going to say the 4 corners of the circle, and you can think I'm a dumb person for saying that, and that's all right. So here are my 4 corners of the circle: 1, 0, 0, 1, negative 1, 0, 0, negative 1. Right? Those are the 4 extreme points on the circle, if you like. The highest and lowest, the furthest right and the furthest left. And those correspond to the angles: 0 radians, pi over 2 radians, pi radians, 3 pi over 2 radians, and all the way around is also 2 pi radians. Now, really, if I was trying to do this as efficiently as possible, I would have only drawn the angle or written the angle and the point I actually care about. So this is the only one I actually care about at the moment, because the angle is pi over 2. And the point is 0, 1. So I know that my xy coordinate is 0, 1. So x is 0 and y is 1. All right, so now I'm just going to use the things I wrote down earlier. I know that sine of the angle is equal to the y value. I know that cosine is equal to the x value. I know the tangent is y over x. So sine of pi over 2 is the y value. Cosine of pi over 2 is the x value. And you can write these in parentheses or not. I wrote x. I should have written what the value was, which was 0. And tangent of pi over 2 is a problem, right? Because tangent of pi over 2 is the y divided by the x, which is 1 over 0. But 1 over 0 is undefined. So I don't like, here's what I would like you to write. You could either write tangent of pi over 2 is undefined, which feels like a lot to write, or you can take the slightly shorter route and write tangent of pi over 2 does not exist. The one thing, and this is a personal pet peeve, it probably doesn't matter to most people. I don't like it when people write tangent of pi over 2 equals does not exist, because that doesn't really make sense to say equals does not exist. So if you could refrain from writing equals there, that would make me just feel good. If you write equals there, I'm not going to mark you off for it. But really, we shouldn't say you're equal to something that does not exist. It just doesn't really make a lot of sense. So that's my own personal take on it. All right, and then the rest of them are the reciprocals. So cosecant of pi over 2 is 1 over 1, which is 1. Secant of pi over 2 is going to be 1 over 0, which also does not exist. Right, so whenever you're dividing by 0, you're getting something, well, I should say, whenever you have 1 over 0 or negative 1 over 0, you're getting something that does not exist. And then finally, cotangent of pi over 2. So tangent is y over x, cotangent is x over y. In this case, that's going to be 0 over 1, and 0 divided by 1 is 0. 0 divided by any non-zero number is 0. Right? How many times does 1 go into 0? Oh, 0 times. In the same way, 0 divided by 6 is also equal to 0, because 6 goes into 0 times. Okay, so this is our method for finding the trig functions of a quadrantal angle. And that's kind of the whole story, to be perfectly honest, but let's do another one. And then I'm going to make an observation. So let's do the 6 trig functions of alpha equal to pi. So again, I'm going to draw my lazy unit circle. And really, I'm just going to draw this point over here, because that's where the angle pi is. And for this point over here, the coordinate is -1, 0. Right? I went 1 to the left, so I went 1 in the negative x direction and 0 in the y direction. So, also, I've definitely seen people in the past get confused as to which one is sine and which one is cosine. So the way I remember it is, right, our point is x comma y, and that's cosine of alpha or theta or whatever, sine of alpha. The way I remember which one comes first is that they're alphabetical. X comes before y, cosine comes before sine, alphabetically. That's an easy way to remember which order they go in. So sine of pi is the y value. The y value is 0. Cosine of pi is the x value, which is -1. And then tangent of pi is 0 divided by -1, which is just 0. And then we have the reciprocal values. So here's the thing. The reciprocal of 0 is always going to be undefined. So if you get 1 over 0, that's undefined. So cosecant of pi is undefined or does not exist. Secant of pi is 1 over -1, which is -1. And cotangent of pi is also going to be the reciprocal of 0. It's going to not exist. Something you might, that's not important, but I just want to point out, technically, if you were writing this out, you'd say cosecant of pi, you'd say, well, that's 1 over 0, which does not exist. Cotangent of pi would be technically -1 over 0, which would then not exist. I don't need you to write that down for me when you're doing these problems, but I just want you to be aware of that. Also, I'm going to do my best to not get scared when my alarm goes off at 2:20, but we'll see. Actually, 2:21 is what I said before. So here's something I have noticed about these. Whenever you're finding the 6 trig functions of the quadrantal angle, here's what you're going to get. You're going to get 2 zeros. You're going to get 2 either +1s or -1s. And you're going to get 2 does not exist. It's always going to happen, which makes sense if we think about it, right? Because I think I've erased what I needed, right? If, let me just write it over here. If sine is equal to y and cosine is x and tangent is y over x and cosecant is 1 over y and secant is 1 over x and cotangent is x over y, well, you're definitely going to get 2 zeros because either x or y is 0. So if x is 0, that one is 0 and that one is 0. If y is 0, that one is 0 and that one is 0. You're going to get 2 does not exist for the same reason, right? If y is 0, then this 1 over y is going to does not exist, and this x over y is going to does not exist. On the other hand, if x is 0, this one doesn't exist, this one doesn't exist. And then finally, you're going to get either 2 positive ones or 2 negative ones, right? If you're over here, cosine is -1, and so is its reciprocal, secant. If you're up here at 0, 1, sine is going to be 1, and so is its reciprocal, cosecant. So you're always going to see this pattern for a quadrantal angle. 2 of the values are going to be 0, 2 of the values are going to be plus or minus 1, and 2 of them are going to not exist. Always, always true. Which is kind of nice. If you're getting stuck with these, you're like, okay, I think I can kind of figure out which one we have to be. How much time? Yeah, okay. Yeah, I should do this one. Okay. Even though. There's one other thing I wanted to point out. So let's say I want to find the 6 trig functions of 11 pi over 2, which is definitely more than a full revolution. So I kind of want to know where I end up. And so here's what I want to point out. You start going around the unit circle, you start to notice some things. So let's say this angle is 0. Now let's use red for the angles. Let's be consistent. So this angle is 0, and then halfway around is pi. And then the full way around is 2 pi. And then another halfway around is 3 pi. And then another halfway around is 4 pi. Each time I go halfway around, I get another multiple of pi. And so on, and so on, and so on. So this coordinate here, the angle is an even multiple of pi. So if someone said, find cosine of 1,000 pi, well, I would know that my angle was right there at the point 1, 0. So I can tell you that cosine of 1,000 pi is 1. Or if someone said find cosine of 999 pi, I know that's an odd multiple of pi, so I know I'm over here, where the value would be -1. The top and the bottom of the circle are a little bit more challenging. The top, right, my angle is pi over 2. And then if I go a whole pi down to the bottom, that's going to be 3 pi over 2. and then back around to add another pi. Pi plus 3 pi over 2 is 5 pi over 2. Right, I'm just adding 2 pi over 2 each time. So then back down here is 7 pi over 2. And then back up here is 9 pi over 2. And then back down there is 11 pi over 2. And so on and so forth. So these are odd multiples of pi over 2. And they just kind of alternate. So 1 pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, 9 pi over 2, 11, 13, 15, 17, okay, I look like a great person. So if I was trying to figure out where 11 pi over 2 was, I'd probably just do it this way. I'd be like, well, I know 1 pi over 2 is here, and then 3, and then 5, and then 7, and then 9, and then 11. There's probably a more efficient way of doing it, but this seems not too terrible. So I'm down here at the point 0, -1, where I know that sine of my angle 11 pi over 2 is going to be -1. And cosine of 11 pi over 2 is going to be 0. And tangent of 11 pi over 2 would be this divided by this, which does not exist. And then cosecant of 11 pi over 2, the reciprocal of -1 is -1. The reciprocal of 0 is undefined, so secant of 11 pi over 2 does not exist. And then I don't really want to say that the reciprocal of does not exist is 0. What I really want to say is just that we know that cotangent is going to be 0 over -1, which is 0. Okay. So that is how you evaluate quadrantal angles using the unit circle. The other thing the unit circle gives us is some insight into some trigonometric identities, some of which I've kind of already alluded to, some of which I haven't. So you're going to see this particular picture kind of a lot. So here's my good old unit circle again. Gotten pretty good at drawing circles in my many years of teaching. That one looks all right. And again, we're going to do the thing where we say, here's my angle theta. And this point here, xy, is equal to cosine theta sine theta. So the x value is cosine of that angle, the y value is sine of that angle. And again, if I drop perpendicular, the base of the triangle is x, the height of the triangle is y, and the radius or hypotenuse, the radius of the circle, which is the same as the hypotenuse of the triangle, is 1. And I'm going to try and write all these down here. So of course we have the definitions we already talked about. Sine of theta is y, cosine of theta is x, tangent of theta is y over x, cosecant of theta is 1 over y, secant of theta is 1 over x, and cotangent of theta is x over y. So what I'm about to write down are what are typically, or maybe at least what I call the quotient identities. So basically any identity that has to do with a fraction. So here are the quotient identities. So probably the ones that I use the most and that you will use the most is the following. Tangent of theta is y over x, which is just sine over cosine. I use that one a lot. And similarly, cotangent of theta is x over y, which is just cosine over sine. I should say cosine theta over sine theta. So these are two of the most used quotient identities, but there are actually 6 more. Really, there's 3 more than those 3 we normally use. But that's not true. We sometimes use them. So the other ones we have, I think, are ones you guys already know. You already know that cosecant is the reciprocal of sine, right? We've said it like 100 times. But you can see it here. Cosecant of theta is really 1 over y, which is sine of theta. So cosecant of theta is 1 over sine of theta. And secant of theta is 1 over cosine of theta. And cotangent of theta, this one might be a little bit harder to see. I'm going to write it out. Cotangent of theta is x over y. But you could also think of that as 1 over y over x. But y over x is tangent of theta. We're really just writing out the reciprocal relationships again, right? We already knew that cotangent was the reciprocal of tangent. We're just saying it again. Okay, and then you can write them in the reverse way as well. You can say it's kind of usually less used, but sine of theta is equal to 1 over cosecant of theta. Right? 1 over cosecant is 1 over y, and 1 over y is just y, which would be sine. Similarly, cosine of theta is 1 over secant of theta, and tangent of theta is 1 over cotangent. So sometimes when we're trying to manipulate a trigonometric expression, it makes a lot of sense to replace a function with its 1 over its reciprocal function. Usually these are the ones we use more, right? Like if I see cosecant, I'm often going to replace it with 1 over sine. We don't use these ones as much. It is less common to say, oh, sine is equal to 1 over cosecant. Although, not that we never use it, just it's less. These two, we use all the time. I would say these two and really these two are the most important ones on this side. How much time have I got? Okay, I got 9 minutes. That's plenty of time. So those are the quotient identities. And then I guess I really want to erase that, but I'm not gonna. I was a little late posting the video for class last night. Sorry about that, in case you were trying to find it. I will definitely get this one posted as soon as the office hours after class end, because the video doesn't start uploading to me until the office hours are over. So the other identities we have are what are known as the Pythagorean identities. And they get their name for good reason. So there's my angle, there's my triangle. So Pythagorean identities come from the Pythagorean theorem. In this right triangle, I could say x squared plus y squared equals 1 squared, which is just 1. But then x is cosine and y is sine. So I could really say cosine. So you could write cosine theta quantity squared, but the more simple way of writing it is cosine squared theta plus sine squared theta equals 1 squared is 1. And I'll just say over here, right, cosine squared theta means cosine of theta quantity squared. It's just an abbreviation that we like to use because it's faster to write. Okay. So that is kind of like, of all the trig identities, that's probably the biggest one, the one that gets cited the most, used the most often. I will often refer to it as our favorite trig identity because it is our favorite. It's the one that we use the most. You could also write it as sine squared theta plus cosine squared theta equals 1. It doesn't really matter which order you write them in, but sometimes it makes more sense to use one over the other. There are a couple alternate versions. So if I subtract sine squared from both sides, I can say cosine squared theta equals 1 minus sine squared theta. And if I subtract sine squared from both sides, sorry, cosine squared from both sides, I can say sine squared theta equals 1 minus cosine squared theta. And then I will just point out, because this comes up often, 1 minus sine squared factors as 1 minus sine theta times 1 plus sine theta. And similarly, 1 minus cosine squared theta factors as 1 minus cosine theta times 1 plus cosine theta. So often you will see people kind of jump straight from saying, oh, 1 minus cosine to 1 plus times 1 plus cosine is equal to sine squared, right? They kind of make a big leap there sometimes. Okay, there's two other, oh, actually, time, okay, time. So before we do the two others, I want to, sorry, I'm moving a little quickly here. I'll try and post the video in case you want to go back and see something I said. So I want to verify that it is true that cosine squared theta plus sine squared theta equals 1 for theta equal to pi over 6. So all I'm going to do is I'm going to start with the left-hand side. So I'm going to do cosine squared of pi over 6 plus sine squared of pi over 6. And I'm not going to say it's equal to 1 yet, even though it should be, because I don't know that yet. I'm just going to work on this side until I get to the other side. So what's cosine of pi over 6? So when I'm thinking about pi over 6, I'm like, oh, that's kind of the small angle. Cosine is the x value, meaning if it's the small angle, I'm going further out in my unit circle. So it should be the larger value. Cosine is the square root of 3 over 2. And it's getting squared. If cosine is the square root of 3 over 2, what does sine have to be? I know I haven't asked you guys anything all day. Anybody want to talk about sine?
1/2.
Yeah, thank you. Because like if we wait, he'll just say it himself because he's almost out of time. It's true, I won't say that. So then this square root of 3 squared is 3, 2 squared is 4, 1 squared is 1, 2 squared is 4, and 3/4 plus 1/4 is 4/4, which is 1. So yes, this definitely works for this value. And it would be actually true for any value. So I didn't put any of these problems on this homework assignment, but I'm probably going to put some on the next homework assignment because it's kind of good to know how this works. Let's go back to the other side. Yeah, that works out. So there are two other Pythagorean identities that I want you to be aware of. And they actually both come from this original identity. So what we're going to do is we're going to take this identity and we're going to divide everything by cosine squared theta. So here's what I get. Cosine squared theta divided by cosine squared theta plus sine squared theta divided by cosine squared theta equal to 1 divided by cosine squared theta. Cosine squared theta divided by cosine squared theta is just 1. Sine squared theta divided by cosine squared theta, well, sine squared over cosine squared is just sine theta over cosine theta quantity squared, which is just tangent theta quantity squared, or tangent squared theta. So that's tangent squared theta. 1 over cosine is secant of theta. So 1 over cosine squared is secant squared theta. So there's another Pythagorean trig identity. 1 plus tangent squared theta equals secant squared theta. A student one time told me the way they remember it is by saying, I tan and get sexy. unforgettable. You cannot forget it. I have tried to forget it. It won't go away, but it's very memorable. So if you have to remember this one, I Can Get Sexy is definitely one way you can remember it and kind of fail to forget it ever, even if you want to. The other one we get by dividing by sine squared. If I divide by sine squared theta, I'm just going to do it because we're almost out of time. Sine squared over sine squared is 1. Cosine squared over sine squared, well, cosine over sine is cotangent. So I get cotangent squared theta. And then 1 over sine is cosecant. So 1 over sine squared is cosecant squared. This one I do not have a fun saying for it. It just is what it is. This one, I feel like this one you use more, this one you use less, but they're both are important. So I wanted to do, yeah. So I'm going to do one more problem. I know it's 2:20, but there's some homework questions. I know the next homework assignment isn't due until Tuesday, so we can definitely revisit this on Monday. But I want to give you one example so you can kind of try and do some of the, I think that's the last 3 problems on the next homework assignment. So let's look at, say, this one. So I want to use the trigonometric identities we just talked about to simplify this expression, 1 minus cosine of x times cosecant of x plus cotangent of x. Simplify this to one term. And so the idea is to use all the things we just learned. So here's how I failed. Still got scared by my own alarm. So I'm gonna do this real quick. Here's how I would do this. And there's not one only right way to do this. There's probably many ways to do this. I'm gonna rewrite cosecant and cotangent in terms of their sines and cosines. So my usual method is to say, okay, cosecant is 1 over sine of x. Cotangent of x is cosine of x over sine of x. It's not always the way to start, but it's how I often start. And then these happen to have a common denominator, so I'm going to put them together. So this is going to be 1 minus cosine x times 1 plus cosine x all over sine of x. I can think of this as 1 minus cosine x over 1, so that I can multiply these fractions together. So when you multiply fractions, it's top times top, bottom times bottom. So this is going to be top times top is 1 minus cosine x times 1 plus cosine x. Bottom times bottom is 1 times sine x. And then we saw before, when you multiply 1 minus cosine times 1 plus cosine, the middle terms cancel out. Right? You get 1. You get a plus cosine and a minus cosine. Those are going to cancel. And then you get a minus cosine times cosine, which is a minus cosine squared x all over sine x. And then 1 minus cosine squared x is equal to sine squared x over sine x. And then one of the sines cancel, right? Sine squared, that's just sine x times another sine x all over sine x. You cancel one of those and one of those and get just sine x. So that's the idea for problems like that at the end of the next homework assignment. You're trying to use the identities we just talked about to simplify down your expression to just being one term. All right, as usual, I've talked too long. I will stop there.